In this video, we will learn about the resonant vibration and resonance. So, an object is said to execute resonant vibration when it vibrates under the influence of an external periodic force whose frequency is exactly the same as the natural frequency of the object. Thus, we can say that resonant vibration are a special case of forced vibration itself, in which the natural frequency of the driven is exactly equal to the frequency of the external driving force. Now, for resonant vibrations, the amplitude of the vibration is maximum, and theoretically, it is found that amplitude should be infinite provided that there is no damping. However, in practice, some damping is always present, therefore, the amplitude of vibration is huge but never infinite. Because some damping is always present because air resistance, because we cannot do everything in vacuum. In natural or normal cases, we do it in atmosphere, and air resistance and friction is always there. Now, the phenomena of increase in amplitude of vibration of a driven object when the frequency of a periodic driving force is equal to the natural frequency of the driven object is called resonance. So you can write this in your definition as well. Now, there are some example of resonance. So you can see a child swing. Okay. So when a child is swinging, on giving periodic push to the child, suppose the child is swinging, the child is sitting over here like this. This is the swing. Now, when there is a periodic push given to the child in the same direction of the swing, then the amplitude of swing goes on increasing after every swing. You might have experienced this yourself and it becomes very large. Second is a resonance in tuning fork. So we take two identical tuning fork, that is A and B, as you can see in this picture as well, of the same frequency, and mount them on two separate sound boxes. So these two are separate sound boxes whose open end are facing each other. Okay, like this. Now we strike a prog on a tuning fork A. Let's say this is striked, okay, with a rubber pad, so that it will start vibrating of its own natural frequency. We will observe that the tuning fork B also start vibrating, as frequency of B is that of frequency of A. So resonance occurs and a loud sound is heard. Now, resonance in air column. So we take a glass burette and a clamp. It is vertically in the stand. Now we fill it completely with water. Now we bring a tuning fork just above the free end of the burette and hold it horizontally like this. Now at the same time, if we open the stop cock of the glass burette so that water start coming out of the burette at a very slow rate, and the water level in the burette, that is this, starts falling. Now, in this case, as the water level in the burette goes on falling, the length of the air column goes on increasing. That is this column, that is air column. This length will go on increasing as the water will get drained from air. Okay. Now, at a particular length L of the air column, or for a particular position of water level in the burette, you listen a loud sound. Now, this loud sound is heard on the account of resonance phenomena, and it happens when the natural frequency of the vibrating air column become equal to the frequency of tuning fork. Okay. Now, if the water from the burette is further allowed to come out below the level of the water in which the loud sound is heard, then the water level in the burette will fall and the length of the air column will increase further. So the resonance is disturbed and intensity of the sound will fall. Okay. Now only at one stage we will have that the resonating air column will have a frequency equal to the resonating of the tuning fork, and in this state and in this length of the burette we will heard a loud sound. Now another example can be resonance in stretched string sonometer. So sonometer consists of a hollow wooden box W with some few holes on one side of it. Now on the top of this wooden box we will have a frictionless pulley P fitted on one end and a peg G fitted on the other end. Now one end of the string, that is a metal wire, is tied to the peg like this, and the other end passes over the pulley. Now a hanger H is suspended from the free end of the wire. Now by placing the slotted weight, that is this weight, on the hanger, we will have a T tension inside the wire. Okay. Now, K1 and K2 are the two wedges over which the wire is tightly stretched. By varying the position of these wedges over here, like this, the vibrating length of the wire can be changed. That is, this length can be changed because this much of the part of the wire is vibrating. Now, if we take a tuning fork which is vibrating and bring it near the sonometer wire, now the wire will start executing forced vibration and a faint sound is produced. Now, if I hold on the vibrating tuning fork near the wire like this, and then I adjust the vibrating length of the wire by moving the wedges in any of the direction required. Now, for a particular vibrating length, say L, the natural frequency of the vibrating wire will be equal to the frequency of the tuning fork. Now, at this stage, resonance will occur and we will hear a loud sound. Okay. Now, a loud sound is heard. Moreover, if a small paper rider is placed over the wire, it falls down due to the large vibrational amplitude of the wire at resonance. I hope this topic is clear to you. Thank you.